Hello, I'm Dr. Maurice Dupre, and in this section we're going to discuss tangent vectors and normal vectors. Okay, here we're basically dealing with ways to study the geometry of curves in space. So if I have a curve in space, the first thing I do would be parameterize it. So let's assume our position is parameterized by a function r of parameter t, and let's think of it as time. And so in this picture, here's the curve. And so by parameterizing that curve, what in effect we do is make that curve the path of a motion through space. And of course, as far as the motion is concerned, it could be speeding up and slowing down, speeding up and so forth. And what we really are interested in is the actual geometry of the curve itself. So we somehow have to standardize, in effect, what happens with this motion. In other words, as far as the curve is concerned, the fact of speeding up and slowing down as we move along it is immaterial to the curve itself. So here in this picture, I've shown with this arrow cross-hatched in red, it's coming out of the blackboard at us. That's our position at time t. And by capital T, parenthesis t, that we use to denote the unit tangent vector to the curve. So it's tangent to the curve, but it has unit length. And here I've shown n of t is the unit normal vector. And so to get the idea of the geometry, notice this curve is, think of it as this is wiggling like this back and forth in space. So as the position moves by that point, the curve is kind of bent like that, and the normal vector sort of tries to get as close as possible to the plane of that motion that would contain that motion, if it's possible. And the unit tangent, of course, is tangent to the curve, and so the unit normal and the unit tangent then are, in fact, turn out to be perpendicular to each other and are part of the description of the geometry of the curve. So what we want to do is see exactly how we make those definitions precise. So remember, thinking of it as a motion, the velocity at time t, which we denote by v parenthesis t, that's the derivative r prime of t, or dr dt. The acceleration at time t is a of t, which is the derivative velocity, so that's dv dt. That is, a is v prime, or r double prime. That's the second derivative, d square r dt square. So first off, remember our derivative vector is tangent to the curve. We're interested in a unit vector tangent to the curve because that's the only thing material to the geometry of the curve. So what we do is we take the velocity vector, which we know to be tangent to the curve, and divide by its length. Then that's the capital T at parameter t is simply v at t divided by the length of v of t. Now, here, the unit tangent vector, remember, as we move along the curve, of course, the direction of our unit tangent vector is changing. So if we were to imagine that unit tangent vector with its tail at a fixed point, here it's moving about on a sphere of radius 1 centered at the origin, if I put the tails all at the origin, and we know for such a motion that its derivative is perpendicular to itself. So when I differentiate the unit tangent vector, I get a vector perpendicular to the unit tangent vector. And so that's how we define the capital N of t, which is the normal vector, n for normal. And so n of t is t prime of t divided by the length of t prime of t. Now, since t of t equals 1, and since n of t is parallel to t prime, we know, therefore, n of t is also perpendicular to t of t. That is, the unit normal vector to the curve and the unit tangent vector to the curve are themselves perpendicular to each other at each value of the parameter t. Okay, what does this actually mean then for our description of the curve? I'm going to use a script v of t to denote the length of the velocity vector, and of course, thinking in terms of motion, that's speed. So consequently, the velocity vector itself is script v times its unit tangent vector times the unit tangent vector in the direction of the velocity vector. And so that suppressing the independent variable t makes a very short equation to remember. And so let's differentiate using our differentiation rules. A is v prime, and now use the product rule. Derivative of the first factor, that's script v prime times capital T, plus v times the derivative of the second factor, capital T prime. So there's our acceleration, and notice because t prime is length of t prime times the unit normal vector, that gives us an equation for A expressed in terms of a scalar function times the unit tangent vector plus another scalar function times the unit normal vector. And so consequently, writing A subscript t for the coefficient of capital T and A subscript n for the coefficient of capital N, what we see is the acceleration vector lies in the plane determined by t and n. So for instance, if my curve is an arc shown by my hand here, notice at the instant I pass this point right here, the unit tangent vector points that way, but the acceleration would be inwards like this. It almost looks like a piece of a circle, and so the acceleration vector points in that direction, and so the acceleration is in the plane of the tangent vector and the normal to the curve at that point. Now, for calculations, these formulas aren't completely convenient. For instance, we can say that the tangential component is the derivative of the speed, that is d over dt of length v. But as far as the normal component is concerned, it's best to calculate it by just computing the cross product of the velocity and the acceleration, take the length of that vector, and divide by the length of vector v. Now, why is it the case that this formula holds? Notice if I take this factor of length v and put it inside here, I have vector v divided by length v. So another way to think of this is the normal component is the length of capital T cross A. So what would happen if I cross capital T with A here? So I'm going to put for the moment here just to in parentheses with our little circle, let's use that. I want to cross both sides of this equation with t. Notice t cross t is 0, and so consequently that term will drop out on the right, and the only thing I get is a sub n t cross n. But remember, t and n are unit vectors, so t cross n is also a unit vector, and consequently when I take the length of t cross a, I just get the coefficient of the t cross n, which is the a sub n. So the a sub n reduces simply to length v cross a divided by length v. So this is the way we'll do our calculations. And one more thing to keep in mind, the computation of the normal vector itself can get lengthy because here you've got to compute the derivative of the speed and then divide that into the derivative vector itself. And here's one thing to keep in mind. If you know the a sub t, if you know the capital T, if you know the a sub n, and you know the a, then using this equation, you can solve for capital N. And since you have a simple expression for a sub t, a simple expression for a sub n, and of course you know a right after you've differentiated the velocity function itself, consequently in this formula the most immediate things are the a sub t, the t, and the a sub n. And so you just solve it for n, for the capital N, to find the normal vector. Okay, so now you can see how all these are related and how they relate to the geometry of the curve. In effect, the specific motion becomes sort of obliterated when we make the calculations of the unit tangent vector and the unit normal vector, but then we can turn it back around and use those to help us describe the velocity and acceleration. So the velocity acceleration, the velocity is the speed times the unit tangent. And the acceleration has a tangential component as well as a normal component. For instance, if I'm driving a car on a racetrack, when I push my foot down on the accelerator, that increases my speed, so that's increasing at the instant I speed up. That's causing me to accelerate along my path. That's a tangential component, but also in effect, because my path may be turning, there's a normal component which is purely relates to how I'm turning. And you're in the car and you feel yourself being pushed over to the door as the person driving makes a left turn, then what you're feeling is in effect the normal component of acceleration. All right, now that we've seen how the definitions of the unit tangent vector and the unit normal vector work and how we can compute the various components of acceleration, let's actually apply this in a specific example. So here in this example, we want to find the velocity at time t, the acceleration at time t, the unit tangent vector at time t, the unit normal vector at time t, the a sub t function and the a sub n function for the curve parameterized as r of t equals 3 square root 2t times I plus e to the 3tj plus e to the negative 3tk. So remember, the main thing to do here is to begin by calculating the derivatives. So I want to calculate the velocity, which is r prime. And so let's come over here, and v of t is r prime of t. So derivative of square root 2 times 3t is just 3 root 2 multiplied by I, plus derivative of e to the 3t, that's 3e to the 3tj. And then when we differentiate e to the negative 3t, we get a negative 3 out front. So we have negative 3 e to the negative 3tk. So there's our velocity vector. And what about our acceleration vector? A of t, of course, is the derivative of the velocity. So here's a constant, so its derivative is 0. Here we're going to get another factor of 3 coming out. Derivative of e to the 3t is 3e to the 3t, and so we already have a 3 there. That makes 9e to the 3t. And now a negative 3 times negative 3 is also a plus 9. Whoops, I've got to write my vector. Don't forget to put the vector in, that constant j. So we have plus 9 e to the negative 3tk, and there's our acceleration vector. So here's velocity and acceleration. Now the next thing we have to do is compute the length of the velocity vector, which I'll just simply denote length v for short. And so what's that? That's the length of this vector. Remember, the square root of the sum of the squares of the components. So when I square 3 root 2, I get 9 times 2, or 18, plus 3e to the 3t quantity squared. And when I square that one, of course, that negative sign is obliterated, and that becomes 3e to the negative 3t quantity squared. Now, we could go ahead and square these out. This would be 9e to the 6t plus 9e to the negative 6t. But I want to show you something here, because this is a kind of a trick that's often performed in these type of problems that you'll run into. That is, something's been done to make the velocity actually be the square root of something that's a definite square, so that you can get quite a simplification. So let's come over here, and using script v for length of v, that's square root 18 plus 3e to the 3t quantity squared plus 3e to the negative 3t quantity squared. what happens if I square just the quantity 3e to the 3t plus 3e to the negative 3t? Notice I get that squared plus twice the product of these two things. What's the product? 3 times 3 is 9, times 2 is 18, times e to the 3t times e to the negative 3t. Notice e to the 3t times e to the negative 3t is just 1. And so there's the cross term. In effect, what I have here is the square, inside the radical is the square of 3e to the 3t plus 3e to the negative t. And so in fact, what we get is just what's inside the radical. And so that tells me that the v itself is simply 3e to the 3t plus 3e to the negative 3t. Now I can factor out the 3 here, and in this problem, e to the 3t plus e to the negative 3t is going to be kind of central. So consequently, just for simplicity, I'm going to use the symbol w for it. It'll help us to simplify things. Sometimes when there are too many symbols around, you can easily get lost in them all, and so it's useful to pick a simple symbol for something that occurs over and over. So what we have here is the speed is 3w. So what about our velocity vector? Remember, that is 3 root 2I plus 3e to the 3tj minus 3e to the negative 3tk. And so our unit tangent vector, remember, is the velocity vector divided by the speed. And so that is 3 square root 2I plus 3e to the 3tj minus 3e to the negative 3tk. And all this is divided by v, which for short I'll just write as 3w. Remember, w is e to the 3t plus e to the negative 3t. And notice what happens. 3's cancel everywhere. And so we simply get the unit tangent vector can be expressed as square root 2i plus e to the 3tj minus e to the negative 3tk over w, where of course w is e to the 3t plus e to the negative 3t. So now we have our unit tangent vector, and next what we have to do is differentiate our speed to find the tangential component of acceleration. And so the derivative of speed, that's 3 times the derivative of w. Well, what will that be? Derivative of e to the 3t is 3e to the 3t, and derivative of e to the negative 3t is negative 3e to the negative 3t. And so consequently, our tangential component of acceleration, a sub t, is 3 times the quantity 3e to the 3t minus 3e to the negative 3t. And so we've now found an expression for our tangential component of acceleration. What we have to do next now is to compute the normal component of acceleration, which we'll do using the formula that the normal component of acceleration is the length of v cross a divided by length v. So let's do that next. All right, for our curve with parameterization r of t equals 3 square root 2 times ti plus e to the 3tj plus e to the negative 3t times k, we found our velocity is 3 root 2I plus 3e to the 3tj minus 3e to the negative 3tk. We found our acceleration by differentiating the velocity, and so that's just 9e to the 3tj plus 9e to the negative 3tk. And we found our speed, which I've denoted script v, that's the length of vector v, is 3w, where w is the expression e to the 3t plus e to the negative 3t. And so consequently, our tangential component of acceleration, which is the derivative of script v is easy to find here. I just differentiate 3w, which would be 3 times the derivative of that, and so these 3's pull out a 9, and the negative sign changed the sign here, and so we got 9e to the 3t minus e to the negative 3t, this quantity all times 9. That's our tangential component of acceleration, which is a fairly simple expression. Notice it's got this quantity e to the 3t minus e to the negative 3t instead of e to the 3t plus, and then it's multiplied by 9. And so that's our tangential component of acceleration, and next we want to find the normal component of acceleration. Of course, we have a simple formula for that. The normal component is length of v cross a divided by length v. So what I've done here is I've written the vector v in the component form with the angle bracket suppressing the I, j, and k to save space, and likewise for the acceleration vector. And so remember, to form the cross product, the simplest way is to use the determinant method. In fact, just to help us remember, I'll put vertical lines here, and underneath we'll put v cross a equals. Now remember, to get the first component, I'm going to cover up this column and take, for the I component, that is this little 2 by 2 determinant here. That's this product minus this product. Of course, minus this product, notice there's a negative 3 here. That's a negative is positive. So in effect, it's 3e to the 3t times 9e to the negative 3t, which is 27, minus, same thing, e to the 3t times e to the negative 3t is 1, 9 times minus 3 is negative 27, so minus a minus 27 is another plus 27, so we have 27 times 2. Pretty easy there. Now, what about the middle component? We eliminate this central column and do it again, but remember, for the middle component, change the sign of the end result. So I have 3 root 2 times 9, that's 27 root 2 e to the negative 3t for that product. And of course, this one is going to give us a 0, so remember, we have to change the sign there. And for the final component, cover up the last column, and now we're finding for k, the coefficient of k, that's the third component, this little 2 by 2 determinant here. Again, this product will be 0, so it's just the first one, which goes with the positive sign. 3 times root 2, 9e to the 3t, so again we get a 27 root 2, and here we have e to the 3t. Notice now, whereas before we had the e to the 3t in the middle component, right there and there, now the e to the 3t is popped up in the last component, and it's e to the negative 3t that's in the middle component. Well, anyhow, there's v cross a, and so what we have to do is find the length of this vector. Notice we can factor out a 27, and that'll make it easier for us to do this. So v cross a is 27 times the length of what we get by eliminating this. So in other words, imagine we've eliminated this number 27 and this number 27, and concentrate on these. So we take the square root of the sum of the squares of those. So 2 squared is 4, plus square root of 2 squared is 2, e to the negative 3t quantity squared, and plus, again, 2, and this time e to the 3t quantity squared. And so that is the quantity v cross a, length, 27 times this radical. Okay, when we look at what's inside the radical, we might be suspicious that in fact there's a simplification like we did before when we found the speed. In fact, let's look. This term with the e to the negative 3t is the square of the quantity square root 2 e to the negative 3t. This term is the square of the quantity root 2 times e to the 3t. So if I add those in square, what will I get? Well, notice the cross term would be twice the product of these two. E to the negative 3t times e to the 3t is 1. 2 times root 2 is 2 times 2 is 4. So the cross term is the 4, and then the other two terms is the square of that and the square of that. And so that does it. And so consequently, when I go to find length v cross A, what we have is 27 multiplied by the square root of this square. And so consequently, let me just rewrite that. We can factor out the square root of 2. And then we have, factoring out the square root of 2, e to the negative 3t plus e to the 3t, which was w. So there's our expression for v cross A, length, 27 square root 2w. Okay, well now let's review. What was our expression for length v? Because remember, to find the normal component of acceleration, we have to divide the length of v cross A by the length of the velocity vector, or the speed. So what was our speed? Remember, the speed or length of v was 3w. So here we have length v cross A is 27 root 2w, and so our normal component of acceleration is length v cross A divided by the speed, length v, which is 27 square root 2w divided by 3w. And notice the w's cancel. 3 into 27 is 9, and so the normal component of acceleration comes out to be a very simple form. It's simply a constant 9 times the square root of 2. So everything's been quite simple, finally, in the end, even though the calculation is somewhat complicated. So notice now we have the unit tangent vector. We know the tangential component of acceleration, we know the normal component of acceleration, and we know the acceleration itself. And so consequently, we can use our equation for the acceleration in terms of tangential and normal components to actually solve for the unit normal vector itself, which we'll do next. Okay, now for our curve and our motion, we've found almost everything except finally we need the unit normal vector. So let's review briefly, because there are a lot of things to compute here. The velocity, the acceleration, unit tangent, unit normal, tangential component of acceleration, normal component of acceleration for r of t. And we found the velocity by differentiating. We found the acceleration by differentiating the velocity. And notice here for this acceleration, we have 9 e to the 3tj plus 9 e to the negative 3tk. And so for purposes of calculation, let's factor out that 9 and write it like that. So we have 9 times e to the 3tj plus e to the negative 3tk. We have our speed, that's the length of the velocity, was 3w, where w is the expression e to the 3t plus e to the negative 3t. We found our normal component of acceleration is simply 9 square root 2, and we had found our tangential component of acceleration is 9 times the quantity e to the 3t minus e to the negative 3t, which I can write as 9 delta, where delta is e to the 3t minus e to the negative 3t. In other words, the two things that are important here are in effect w, which is the sum of the exponentials, and delta, which is the difference of the exponentials. So the delta comes up in the tangential component of acceleration, whereas the w comes up in the speed. So now let's go to our final calculation. Remember, our unit tangent vector was square root of 2I plus e to the 3tj minus e to the negative 3tk, all divided by w. And the way we'll find our normal component of acceleration is to look at the equation that tells us the acceleration vector A is tangential component of acceleration times t, which we have up here, plus the normal component of acceleration times the unit normal vector n. Notice everything in this equation is now known to us except for capital N. For instance, writing our acceleration vector with the angle bracket notation, it's 9 times the vector 0, comma, e to the 3t, comma, e to the negative 3t. And our tangential component of acceleration, remember, is 9 delta. And so tangential component of acceleration times this vector, capital T, is 9 delta over w times an angle bracket notation, square root 2, comma, e to the 3t, comma, negative e to the negative 3t. And then plus normal component of acceleration, which was just 9 times the square root of 2 multiplied by the unit normal vector. So you see, the only unknown to us in this big, long, complicated expression is just the unit normal vector n. We know the delta is e to the 3t minus e to the negative 3t, and the w is e to the 3t plus e to the negative 3t. So in order to finally solve for n, we can first notice that 9s cancel. And consequently, all I have to do is shift this term to the other side and divide by square root 2. Let's begin by dividing by square root 2. When we do that, that cancels the square root of 2 in front of the n, and then divides each of the other terms by square root 2. So I'll put a square root of 2 in the denominator in front of that term, and we put a 1 over square root 2 out in front of this term. And so notice at this point, our n is sitting over here on the right all by itself, and so all I have to do is move this to the other side. So let's do that. The n is now finally equal to 1 over the square root of 2 times the vector 0, comma, e to the 3t, comma, e to the negative 3t, minus, and what we have here is delta divided by square root of 2w times the vector square root 2, comma, e to the 3t, comma, negative e to the negative 3t. So there's our expression for the unit normal vector. If you wanted it in terms of, all collapsed into one angle bracket expression, you see you just use your vector operations, which we'll do next, and see if we can find any simplifications for our normal vector expression. All right, we've got an expression now for our unit normal vector to the curve. And just to review, it's n equals 1 over square root 2 times angle bracket 0, comma, e to the 3t, comma, e to the negative 3t minus delta over w, angle bracket root 2, comma, e to the 3t, comma, negative e to the negative 3t, angle bracket close. And this is all multiplied by 1 over root 2. That is, we easily factor out the 1 over root 2 from everything. And so that it's easy now to do the vector operations to find the components. For instance, our first component is just negative delta over w root 2. How about our second component? E to the 3t minus delta over w e to the 3t. That's 1 minus delta over w e to the 3t. The last component, e to the negative 3t minus, that's plus, so e to the negative 3t time plus delta over w e to the negative 3t. That in effect is 1 plus delta over w e to the negative 3t. Now that looks fairly simple, but in fact let's go back now. What are delta and w? Remember, delta is e to the 3t minus e to the negative 3t, and w is e to the 3t plus e to the negative 3t. So 1 minus delta over w is, putting a common denominator form, w minus delta over w. And what is w minus delta? If I subtract delta from w, then that will cancel off the e to the 3t terms, and negative e to the negative 3t is a plus e to the negative 3t. So we end up with 2e to the negative 3t in the numerator divided by w. And what about the 1 plus delta over w? Same thing, putting it over common denominator, we have 1 plus delta over w plus delta over w. And so what is w plus delta? Well, when you add these two things, notice these two terms cancel, and I get twice e to the 3t. So the 1 plus delta over w is 2e to the 3t over w. So now let's go put them in. For instance, the 1 plus delta over w multiplying e to the negative 3t. If I multiply this by e to the negative 3t, the e exponential terms cancel, and I've just got 2 divided by w. What about for this one? 1 minus delta over w is 2e to the negative 3t over w. So when I multiply this by the e to the 3t, again the exponentials cancel. I'm left with just 2 over w. And so that means coming up here and putting in for delta and w, the first component is negative root 2 times e to the 3t minus e to the negative 3t over the w, which is e to the 3t plus e to the negative 3t. The second component is 2 over w. That's 2 over e to the 3t plus e to the negative 3t. And the last component is 2 over w, which is e to the 3t plus e to the negative 3t in the denominator there. So finally, our final result, after making some algebraic simplification on these vector operations, is not that complicated. The unit normal vector has maybe a kind of a messy first component, but the second and third components aren't so bad. But in any case, this problem illustrates how complicated the computations can get. You have to be careful, and it helps when you spot something that keeps recurring over and over to choose a symbol for it so that you can simplify your calculations lengthwise. It's very easy in these calculations to get lost in a forest of terms. In any case, the best way to learn this is practice. Practice, practice, practice. So now try some on your own.